Before I actually start looking at the numbers in this sequence, let me just go through our procedure. If there was some way I could remove the influence of an squared, I would end up with just bn plus c, which defines a linear sequence. And the way you do that is to find the second common difference of the series of numbers and halve it. So if the common difference was 4, our coefficient here, a, would equal 2. It's just half of that second common difference. So let's find out what our common difference is. And I think with these questions, the neatness of your layout is incredibly important. So let's write down our sequence with a reasonable gap in between the numbers. So this is our first line, and this is the original sequence. So let's just put that there. So we need the second common difference and find out what that is. So first of all, we need the first difference. And I'm going to put those numbers right in between here. 6 minus 7 is -1. We've dropped 1. Here, 7 minus 6, we've added 1. This is added 3. This is added 5. So now, the second difference. You can see clearly that we're adding 2 every time. So we've found that the second difference is indeed common, and it's 2. So our value for a in the quadratic expression that we need, we've found our first answer. A is equal to 1. So un is equal to n squared plus bn plus c. So we're on our way. Now then, as I indicated before, if I can remove the influence of n squared from our original sequence here, I would end up with a sequence defined as bn plus c. So let me now write down beneath our original sequence numbers what value n squared would be. So when n is 1, n squared will be 1. 2 squared, 4. 3 squared, 9. 4 squared, 16. 5 squared, 25. Now I'm going to subtract 1 from 7, 4 from 6, 9 from 7, 16 from 3, and so on, to generate a new sequence, but it will be a sequence which is defined as bn plus c, which will be a linear sequence. So let's do that. So 7 take away 1 is 6. 6 take away 4, 2. 7 take away 9, -2. 10 take away 16, -6. 15 take away 25 is -10. And yet again, I need the difference. Hopefully I'll get a common difference straight away. 6 going to 2 is a drop of 4. This is also a drop of 4. This is also a drop of 4. And this is also a drop of 4. So using the techniques for a linear sequence, remember this series of numbers is controlled by bn plus c. We've lost the n squared bit of the quadratic equation. So this is bn plus c. So we've now got a common difference of -4. So our series must be based on -4n. But how wrong or right are we? What does -4n generate on its own? It generates on the first term, it generates, when n is 1, -4. And on the second term, it generates -8. We're expecting 6, but our sequence only generates 4. So we would have to add 10 to -4 to bring it up to 6. Let me just go through that again. We found a common difference of -4. So we know that -4n is part of the sequence. So we've effectively got b, but we don't know what c is. You see, -4n on its own, when n is equal to 1, produces -4. But our sequence demands that our value is 6. So we have to add 10. And that turns out to be the value of c. So the results we've got is that b is equal to -4, and C is equal to positive 10. So UN turns out to be n squared minus 4n plus 10. I think it's always a good idea, if you've got time in an exam, just find out whether the quadratic equation you think's the answer generates one of the answers. Let's try n is equal to 3. We're expecting an answer of 7, so UN, according to the question, should equal 7. Let's see what it does generate. 3 squared is 9. Take away 4 times 3, which is take away 12, plus 10. And that's equal to 19 minus 12, which is 7. So that confirms what we suspected, and our answers here stand. So let's have a look at part B. And they're asking us to find the term U20. Well, all we need to do here is shove n is equal to 20 into our formula. So I get U20 is equal to 20 times 20 is 400, minus 4 times 20 is 80, plus 10. And that's equal to 400 minus 80 is 320, plus 10, 330 is what I make it. And that, with any luck, should be your answer.